Let's discuss depth first search. Depth first search uses a stacked data structure compared to breadth first search, which we saw in the previous video, which uses a queue data structure. If we apply DFS on a tree, which is also a graph, a tree is an acyclic graph, right? A graph which contains no cycles is called a tree. So if we apply DFS on a tree data structure, one of the traversals will yield the pre-order traversal. One of the DFS traversals on a tree, which is also a graph, will give us the pre-order traversal. Also, keep in mind that the DFS for a graph is not unique. Starting with a given vertex, we can generate multiple depth first search traversals, and we can also start from any vertex in the graph to generate a depth first search for that particular graph. With this background information, let's try to develop an intuitive approach on how to go about applying DFS on graphs. So we'll start with example 1. Just one point you have to keep in mind when you're doing DFS is that you will try to traverse the depth. By depth, you mean you have to go till the end of a path, and once you reach a dead end, you have to backtrack and look for other possible paths. So let's see how we can go about it. Now, for example number 1, I'll assume my starting vertex. So I'll just tilt this a bit. I'll assume my starting vertex, my start vertex, to be B. Okay, now with B as my start vertex, let's try to generate a DFS traversal. So what will I do? I'll visit the starting node. So my starting node is B. So I'll visit it. Then I look at one of the adjacent vertices of B. How many adjacent vertices of B are there? A is an adjacent vertex, D is an adjacent vertex, E is an adjacent vertex. Why are A, D and E considered adjacent vertices of B? They are considered adjacent vertices because they are directly connected to B through an edge. So I can visit any adjacent vertex of B that I like. So let me visit A. Now in DFS, what we would have done is we would have visited all the adjacent vertices of B. But here we will not do that. After visiting one of the adjacent vertices of B, which in this case happens to be A, we will suspend the exploration of the vertex B and move on to the exploration of vertex A. And how will we suspend this exploration of B? We will suspend the exploration by pushing B on our stack. So I'll show you a complete working where we would employ a stack to carry out DFS. For now, let's continue with the intuitive approach. Just keep in mind that the suspension of exploration of a particular vertex is achieved by means of a stack, because the stack data structure will help us to carry out the backtracking operation. Now, when I'm at A, what will I do? I'll look at an adjacent vertex of A. So how many adjacent vertices of A are there? B, D, E and C, because B, D, E and C, these are all connected to A by direct links. That's why we are saying that these are adjacent vertices of A. Now we will visit one of the adjacent vertices. Out of these 4 adjacent vertices, B has already been visited, so we cannot visit it again. So we are left with D, E and C. Let me visit C. Okay, so I'll visit C and show it in the output. Now what I'll do is I'll suspend the exploration of A. I'll suspend the exploration of A and move on to exploring the next vertex, which is C. Now what are the adjacent vertices of C? The adjacent vertices of C are A, F and G. So I'll visit any one of them. So A has already been visited, so I cannot visit A again. I'm left with F and G. So let me visit F. So if I visit F, then I'll print it in my output. Now what I'll do, I'll suspend the exploration of C. I'll suspend the exploration of C and move on to exploring F. Now I find that F has two adjacent vertices, C and G, out of which C has already been visited. I'm left with G, so let me visit G. Now what I'll do, I'll suspend the exploration of F. I'll suspend the exploration of F and move on to G. Now when I go to G, I find that G has two adjacent vertices, C and F, both of which have already been visited. So what can I do? Now I have nowhere else to go because the adjacent vertices of G have already been visited. So now I'll backtrack. Where will I backtrack? I'll backtrack to the previous vertex. Which is the previous vertex? F. So now I'll look at the adjacent vertices of F again, C and G. But both C and G have been visited. Both C and G have been visited, right? So what will I do? I will again backtrack and go to the previous vertex, which is the previous vertex to F, C. Okay. Now I look at the adjacent vertices of C. The adjacent vertices of C are A, F and G, all of which have been visited. So again I have to backtrack. I'll backtrack to A. Now I'll look at the adjacent vertices of A, B, C, D and E. So I'm left with D and E, which are unvisited vertices. So I'll visit any one of them. Let me visit D. Let me visit D. Now, after visiting D, what will I do? I'll suspend the exploration of A. I will suspend the exploration of vertex A and move on to exploring vertex D. Now, when I go to vertex D, I find that the adjacent vertices of D are B, A and E. Now, out of B, A and E, B and A have already been visited. E has not been visited. So, let me visit E. So, I'll visit E. Now what I'll do, I'll suspend the exploration of D. I will suspend the exploration of D and move on to vertex E. I find that the vertices of E, which are adjacent to E, are A, B and D, all of which have been visited. So I will backtrack. I'll backtrack to D. Now on backtracking to D, I find that all adjacent vertices of D, B, A and E have already been visited. So again I'll backtrack. I'll backtrack to A. I find that all adjacent vertices of A, B, C, E and D have been visited. So I have nothing to do. Again I'll backtrack. I'll backtrack to B because B was my first vertex. So I'm back at B, and on seeing the adjacent vertices of B, I find that all vertices have been visited. So I'll stop my DFS and conclude that this is the traversal. Although I tried to explain this backtracking method, you could have understood that once I have listed out all the vertices, there's no need to check further. So for MCQ questions, once you have all the vertices in your output, you can stop your process. Anyway, let me show you another DFS traversal. Now this time I'll go a little quicker so that you have probably got the intuition by now. So we can list out a few more DFS traversals a bit more quickly. So now I'll assume my starting vertex. I'll assume my starting vertex to be A. So what will I do? I'll start with vertex A. So let me visit vertex A. Now what are the adjacent vertices of A? B, C, D and E. I can visit anyone. Let me visit B. Now after visiting B, I will suspend the exploration of A and move on to B. I find that the adjacent vertices of B, which are unvisited, the unvisited adjacent vertices of B, mind what I'm saying, the unvisited adjacent vertices. The unvisited adjacent vertices of B are D and E. So I can visit any one of them in any order. So I'll visit D first. I'll visit D. Now on visiting D, I'll suspend the exploration of B and I'll start exploring D. Now I find that an adjacent vertex of D, which is unvisited, is E. The remaining two adjacent vertices of D, A and B, have already been visited. So I'm left with only one unvisited adjacent vertex, so I'll visit it. So I'll visit E. Now, when I come to E, I find that all adjacent vertices of E, A, B and D, have been visited. You can see that A, B and D have been visited. So I have nothing else to do. I'll backtrack and I'll go to the previous vertex. Which is the previous vertex? D. Now I'll look at all the adjacent vertices of D. All the adjacent vertices of D are B, A and E, and they have been visited. So I have nothing to do. Again, I'll backtrack. I'll backtrack and go to B. I find that the adjacent vertices of B are A, D and E. Now all of them have been visited. So what will I do? Again I'll backtrack. I'll backtrack and go to A. Now the adjacent vertices of A, B, D and E, these three are adjacent vertices of A. They have already been visited, but C, which is also an adjacent vertex of A, has not been visited. So I'll visit C, and now I'll suspend the exploration of A and start exploring C. Now when I start exploring C, I'll look at the adjacent vertices. The adjacent vertices of C which have not been visited are F and G. So I'll visit one of them. Let me visit G. Now when I'm visiting G, I'll suspend the exploration of C and I'll start exploring G. Now when I start exploring G, I find that there is only one adjacent vertex of G, that is F, which has not been visited. So let me visit that. And now I can find that all 7 vertices have been listed out. That means I can stop my procedure. And you can probably understand what will happen. A few more backtrack operations will take place till your stack becomes empty and the DFS process will come to an end. Okay. Now let's try a DFS on this tree. I'll try to prove to you this statement which I had mentioned earlier, that DFS gives pre-order when applied on a tree. I'll try to prove this statement by applying DFS on this binary tree. Let's see. Now I'll start. Okay, I'll just cancel this out. Let my starting vertex obviously be the root. So my root is the starting vertex. Now I'll start exploring the root. So what will I do? I'll visit the root. I'll suspend its exploration and move on to an adjacent vertex. Now, if you remember pre-order traversal, pre-order is given by root followed by left subtree followed by right subtree. This is how you would list out the pre-order of a tree. So we will see that we are going to apply DFS, but it will turn out that one of the DFS traversals which we will be generating will be same as our pre-order. Let's see. So now I'm doing DFS. I'll forget about pre-order for now, and then I'll just verify at the end whether my DFS matches with the pre-order. So 27. Now the adjacent vertices of 27 are 12 and 30. So I'll visit one of them. Let me visit 12. Now I'll suspend the exploration of 27 and I'll move on to 12. I'll start exploring it. The adjacent vertices which have not been visited of 12 are 8 and 9. So let me explore 8. Let me visit 8 rather. Now after visiting 8, I'll suspend the exploration of 12 and I'll try to explore 8. But there are no adjacent vertices of 8 which have not been visited. So I'll backtrack. I'll backtrack and go to 12. When I go to 12, I find that 9 is the only adjacent vertex of 12 which has not been visited. So I'll visit 9 and I'll suspend the exploration of 12 and start exploring 9. But I find that 9 is an end vertex and its only adjacent vertex 12 has already been visited and it has no adjacent vertices left which have not been visited. So I'll backtrack and I'll go to 12. Now I find that all adjacent vertices of 12, that is 8, 9 and 27 have been visited. So again I'll backtrack and I'll go to the previous vertex which is 27. Now from 27 I find that 30, which is an adjacent vertex of 27, has not been visited. So I'll go to 30 and I'll visit it. So I'll visit 30. Now after visiting 30, I'll start exploring 30 by suspending 27. So I'll look at the adjacent vertices of 30 which have not been visited. Which are they? 50 and 40. So I'll visit any one of them. So let me visit 50. Now after I visit 50, I'll suspend 30 and I'll start exploring 50. I find that there are no adjacent vertices of 50 which have not been visited. So I'll backtrack and I'll go to 30. I find that 40 is the only adjacent vertex of 30 which has not been visited. So I'll visit 40. After visiting 40, I'll suspend the exploration of 30 again and I'll start exploring 40. But I find that there is no adjacent vertex of 40 which has not been visited. That means I've come to a dead end, and see what will happen. I'll again backtrack to 30. Now there are no adjacent vertices of 30 which have not been visited. So I'll backtrack to 27. Now there are no adjacent vertices of 27 which have not been visited. That means I'll put an end to 27 as well, and I'll conclude that this is my DFS. Now you can see that this DFS is same as my pre-order. What would have been the pre-order? See, start from the root. So that's 27. Root left. I go to the left subtree. Now I'll explore left subtree using pre-order. What will I do? Again, I'll go for the root of this subtree. So that will be 12. So I'll print 12. Now I'll go to the left subtree, which is 8. Then I'll go to the right subtree, which is 9. So I have 27, 12, 8, 9. See, 27, 12, 8, 9. Then I'll go to the right subtree. See, after the left subtree, I have to go to the right subtree of 27. In the right subtree of 27, I find a subtree with 30 as the root. So I'll start exploring this subtree with 30 as the root by using pre-order. So I'll print 30, then I'll explore the left subtree of 30, which is 50, and then the right subtree, which is 40. So that is exactly what I've got. So the order which I've got here, the Dfs traversal which I've got here, is exactly same as the pre-order of a binary tree. So this statement has been conclusively proven. Now, just like BFS could have been applied on undirected graphs and as well as directed graphs, DFS can also be applied on undirected graphs as well as directed graphs. So let's see how we can apply DFS on this graph. So you can get many possible traversals. I'll show you one of them. So let my start vertex be, let's say 5. Let's try something different. Let's not start with 1, let's start with 5. Okay, so 5, what will I do? I'll visit my starting vertex and I'll look at the adjacent vertices of 5. So what are the adjacent vertices of 5? The adjacent vertices of 5 are those vertices from which you have outgoing edges. The vertices to which you have outgoing edges from 5 are the adjacent vertices of 5. See, an outgoing edge means from 5 there will be an outward arrow. So there is an outward arrow from 5 to 1, that means 1 is an adjacent vertex of 5. There is an outward arrow from 5 to 2, that means 2 is an adjacent vertex of 5. So I have two options. I can go for either 1 or 2. Let me go for 1. So once I visit 1, I'll suspend the exploration of 5 and I'll proceed to exploring 1. So what will I see? I'll see the outgoing edges from 1. The outgoing edges from 1 are 2 and 6. Now both 2 and 6 have been unvisited. So I can choose anyone. Let me choose 6. Now after going to 6, after visiting 6, what will I do? I'll suspend the exploration of 1 and I'll start exploring 6. Now when I start exploring 6, I find that there are no adjacent vertices of 6. So I'll simply backtrack to 1. Now when I go back to 1, I backtrack to 1, I find that 1 has an adjacent vertex 2 which has not been visited. So I'll visit 2. And I'll start exploring 2 now by suspending 1, the vertex 1 once again. So when I start exploring 2, I find that 2 has an adjacent vertex which is 3. So I'll visit 3. Now on visiting 3, I find that I have to suspend the exploration of 2 and start exploring 3. So I'll start exploring 3. I find that 3 has only one adjacent vertex which is 4. So I'll visit 4. I'll suspend the exploration of 3 and start exploring 4. I find that 4 has one adjacent vertex which is 5 and 5 has already been visited. So I have nothing to do with 4. I'll backtrack and go to 3. Now 3 has no adjacent vertex which has not been visited. So I'll backtrack to 2. Now 2 has no adjacent vertex which has not been visited. Then I'll finally backtrack to 5 because that is what I started with. But the adjacent vertices of 5, 1 and 2 both have been visited. That means I've come to an end of my DFS traversal. Right? So this is how you would develop an intuitive approach to solving DFS. This is very useful when it comes to multiple choice questions. Now I'll take two more examples where the questions will be slightly different, but you'll probably get the hang of things. Let's see how we can do that. Now let's look at this question. See, this has been asked in NET 2007, UGC NET 2007. We have been given 4 options and we have been given a graph, and we are being asked that which of these options out of A, B, C and D, which of these options is correct. So what we have to do is we'll have to examine every option separately and find out which one is correct. So this will be essentially an option checking approach, but even in that case, the DFS intuition which you have probably developed by now will come in handy. Let's try to examine option number 1. So we have to start with A. That's fine. So we are visiting A. Now we are suspending the exploration of A and going to one of its adjacent vertices, which is B. So that is allowed. Now from B, I can go to either D or E because these are the adjacent vertices. From B, I cannot go to C because C is not an adjacent vertex of B. That means, see, after B, they have listed out C. That means this option is incorrect. From B, I can either go to D or E because they are the adjacent vertices. So this option is incorrect. Let's try to examine option B. Now I'm at A, that's fine. I'll visit A. Then I'll go to B, fine. Now from B, I can go to either D or E. That's what I'm doing. I'm going to D. Okay. Now from D, there is a dead end. So I'll backtrack to B. Then from B again, I can go to E. So I'm going to E. That's up to this point, it's fine. Now from E, I can go to F. F is an option and that is what they've shown here, F. Fine. Now from F, I have an option of C. and they have shown C. That means this option is correct. Now, since only one option happens to be correct, this is the correct answer. But let's examine this as well, this option, for completeness. So we'll start off with A. Now C is an adjacent vertex, so I can go to C. So up to this point it's fine. This is correct. This is correct. Now from C I can either go to E. In fact, I can go only to E. So from C I'm going to E. So up to this point it's fine. Now from E I can go only to F. But from E they have shown B. But that's not allowed because E is not adjacent to B. Or rather I should put it this way, that B is not adjacent to E, because had B been adjacent to E, if B had to be adjacent to E, then from E there would have been an outgoing edge to B. But there is no outgoing edge from E to B. There is an incoming edge from B to E. To E you have an incoming edge from B. You don't have an outgoing edge. If you had something like this, then there would still have been a possibility. But since you don't have this outgoing edge, from E I cannot go to B, and this option is incorrect. Okay, fine. Now let's examine this question. Let's examine every option one at a time. So the first option, we are starting off with A. Okay, fine. Now from A I can either go to B, C or D. So they are going to B. Fine, I'm going to B. Now from B I can go only to E. So from B they are going to E. Okay, that's allowed. Now I'm at E. Now from E I can go to H, because it's the only unvisited adjacent vertex of E. See, B is also an adjacent vertex of E, but B has already been visited. So I can go to H now. So I'm going to H. Now from H I can go to I can only go to F, because E has already been visited. So from H they're going to F. From F I can go to either C or D. Now from F what they're doing is they're going to C. Okay, so that's allowed. Now from C the adjacent vertices are A, E and F, all of which have been visited. So what will I do? I'll backtrack and go to F. Now from F I can go to D. That is exactly what they've done. So this order is perfect. Now let's examine the second one. In the next case I have the starting vertex as D. Now D is my starting vertex, fine. So from D I'm going to F. That's allowed, no problem. From F I can go to C or H, because they are unvisited. From F they're going to C. So even that is allowed. Now from C they're going to A. Okay, that is allowed. Now from A they're going to B. Even that is allowed, because B has not been visited. From B they're going to E. Fair enough. And from E they're going to H. Even that is allowed. So this is allowed. Now I'm starting off with C. Okay, let's start off with C. From C, so I'm visiting C. I'm suspending C and going on to an adjacent vertex. They're going to F. That's allowed, because F is adjacent to C. Now from F they're going to D. Okay, D is adjacent to F and it has not been visited, so that's allowed. From D they're going to A. A is adjacent to D, so that's allowed. From A they're going to B. B is adjacent to A, so that's allowed. From B they're going to E. E is adjacent to B, so that's allowed. From E they're going to H. H is adjacent to E, so even that is allowed. So even this traversal, this Dfs traversal is allowed. Now let's start with H. Okay, we're starting off with H. From H they're going to E. Okay, so we're starting off with H. From H to E. E is adjacent to H, so this is allowed. From E they're going to C. From E you can go to C, so that's allowed. From C they're going to F. From C they're going to F, that's allowed. Now from F they're going to A, but F is not connected to A. F and A are not adjacent to each other, so I cannot go from F to A. So this is incorrect. Now next, I'm starting off with A. Fine. From A they're going to C. From A to C, yeah, that's allowed. Now from C they're going to F. From C to F, even that is allowed. From F to H. From F to H, okay, allowed. Now from H to E, allowed. From E to B, allowed. From B to D, okay. Now from B, the only adjacent vertex of B is A, which has already been visited, so I'll backtrack and I'll come to E, fine. Now from E, I have B and H, but B as well as H have already been visited, so I'll backtrack and go to H. Now from H, the adjacent vertices are E and F. E as well as F have already been visited. So again I'll backtrack and go to F. Now from F I have C and D and H. Now out of C, D and H, only D has not been visited, so I can visit D and bring my DFS to a close. So this is allowed. Now let's examine this. Starting off with B, fair enough. From B they're going to A. From B to A, fine, allowed. From A they're going to C. From A to C, okay, allowed. From C they're going to F. From C to F, fine, allowed. From F they're going to D. From F they're going to D, okay, allowed. From D they're going to E. From D they're going to E, but no, that cannot be done. See, what are the adjacent vertices of D? The adjacent vertices of D are A and F. Okay, let's see. See, the adjacent vertices of D are A and F. Now both A and F have already been visited, so I can backtrack. Now let's see, there's still a possibility. So I'll backtrack and I'll come to the previous vertex, which is F. Now the adjacent vertices of F are C, D and H. Now out of C, D and H, D has already been visited, C has already been visited, but H has not been visited. So from F I should go to H, but the next vertex that they're visiting is E. But from F I've backtracked and come to F. From F, see, I've backtracked and I've come to F. From D I've backtracked and come to F. From F I can easily visit H because H has not been visited and F is adjacent to H. So this part is causing the problem and this is not a valid DFS traversal. Okay, so this is how you can solve questions where you have been given options and you're asked to check for correctness. Now what I'll show you is a comprehensive example where I'll employ a stack and show you the steps of how it's done. Okay, so let's say you have been given this graph. Let's label this graph. Okay, let's call this graph G. Now I have to apply DFS. I can assume any vertex to be my starting vertex. Let's say I'm assuming the starting vertex, I'm assuming the start vertex or the starting vertex to be A. And now I'll show you how a stack is used to carry out the DFS traversal. So I'll show you the step-by-step operations. So let's see how it's done. So step 1. Now at every step I'll have to maintain a stack as well as, so I'll maintain a stack which grows upwards. So this is my stack. I'll maintain a stack and I'll maintain, okay, let me call this stack, and I'll maintain an array called visited. I'll maintain an array called visited. So how many vertices are here? If you count 1, 2, 3, 4, 5, 6. There are 6 vertices. So there will be 6 slots in my visited array. So 1, 2, 3, 4, 5, 6. There are 6 slots in my visited array. This array is called visited. Now, what are my slots? So let's label the slots. Let's say this is the slot for A, B, C. In fact, pardon my mistake, there is no C. There is a G vertex. So let me label it as G. So that's A, B, G. There is H, there is E, and there is F. Okay, so there is one slot for every vertex. Now my starting vertex is A, and let's say this is my output. Let me show you the output. Okay, where should I show the output? I can show it here, I think. Yeah, I think this is a feasible place to show the output. So first thing that I'll do is, what is my starting vertex? My starting vertex is A. So I'll visit it. And in the visited array, I'll mark it as visited by setting it to a value of 1, by setting its location with a value of 1, and I'll output it. Now, this is the initial step. Now it's time to show you the repeating steps. Now, what are the adjacent vertices of A? The adjacent vertices of A are E, F, and B. You can find, programmatically, you can find the adjacent vertices by scanning the graph representation of this graph. You can, or let's put it this way, you will take this graph and you will represent it in your computer using either an adjacency matrix or an adjacency list. So from that adjacency matrix or the adjacency list, you can easily find the vertices which are adjacent to a given vertex. My given vertex here is A. So from the adjacency matrix, I can find that the adjacent vertices of A are E, F, and B. E, F, and B are the adjacent vertices of A. So what will I do? I will choose one. So which one will I choose? I'll choose, let's say I choose E. So I choose E, and now I'll start exploring E. I'll suspend A. How will I suspend A? I'll suspend A by pushing it on my stack. So I'll push A on my stack and I'll suspend its exploration. And now my current vertex, let me have a variable called current, which was initially A, is now changed to E. My current vertex has now become E. Okay. Now what will I do? I will start exploring E. Okay. Now you will have to show the stack at every step. So I'll show a few steps, then I would expect you to make the necessary notes. Okay. I'll show you what is to be done. So in step 2, again, you will have to show the stack. So let's say this is your stack. Okay. This is a bit clumsy here. Please pardon me. Sorry for the mistake. And let me just complete my stack diagram. Yeah, that's, I think, a big enough stack. Just ignore this part, okay? There's nothing here. So initially my stack contains A. And this is my visited array. So again, you have to show at every step, you have to show the stack as well as the visited array. So there are 1, 2, 3, 4, 5, 6. There are 6 slots for A, B, G, H, E, and F respectively. So A has already been visited. Now my current vertex is E. Now what will I do? I'll look at the adjacent vertices of E. What are the adjacent vertices of E? A, F, and G. Now I can show you the adjacent vertices every time. So it's now A, F, and G. These are the adjacent vertices of my current vertex E. What will I do? I'll see which of these vertices has not been visited. So I can see that A has already been visited, so A is not an option. I'm left with F and G. So I can choose either F or G. Let me choose F. Now, before choosing F, what will I do? Since E is my current vertex, I will visit it. I'll visit my current vertex, which is E. I'll mark it as visited, and I'll show it in the output. And now, once I choose F, F becomes my current vertex. I will suspend the exploration of my current vertex. My current vertex was E. I'll suspend its exploration by pushing it on the stack. And now I'll move on to F. I'll start exploring F. Now what I'll do is I'll not show the stack or the visited array separately, but remember, for every step you have to show the stack, the visited array, possibly the list of adjacent vertices, as well as your current vertex at every step from your examination perspective. Okay, please keep that in mind. And while you're taking down notes from this video, please show every step. Please pause the video from time to time and prepare every step separately. Okay, fine. Now moving on. Now my current vertex is F. What will I do? I'll look at the adjacent vertices of F. What are the adjacent vertices of F? So my W will now change. Adjacent vertices of F are A, B, H, and E. So they are A, B, E, and H. These are the adjacent vertices of my current vertex F. Now, out of these 4, I find that A and E have already been visited. I'm left with B and H. So what will I do? I will choose any one of them. Now, before choosing them, since F is my current vertex, I will output it by visiting it. So I'll mark it as visited. And now I'll choose out of B and H one of these 2 vertices to be my current vertex. Let me choose B. So B becomes my current vertex. I'll suspend the exploration of F by pushing it on the stack. Now B is my current vertex, right? Okay, this was step number 3, right? Now I'm at step number 4. So with B as my current vertex, again, my job is to look at the adjacent vertices of B. So what are the adjacent vertices of B? If you see, let me just tilt the page for you. It will be a bit easier for me to write. So the adjacent vertices of B, this is the adjacent vertex of B. These were the adjacent vertices of F. These were the adjacent vertices of E. Okay, the suffix denotes the vertex for which I am listing out the adjacent vertices. Now for B, the adjacent vertices are F, A, H, and G. So the adjacent vertices of B are A, F, G, and H, right? See, A, F, H, and G. So these four are my adjacent vertices of B. Now, out of these four adjacent vertices, I find that A has already been visited. From the visited matrix, from the visited list, I find that A has already been visited. I find that F has already been visited. And I find that G and H have not been visited. Now, before moving on, what will I do? I will mark B as visited. Since B is my current vertex, I'll visit it by marking it with 1 in my visited array, and I'll also output it. I'll output B. Now the remaining vertices which are adjacent to B are G and H. Out of these two, I'll have to choose one as my current vertex by suspending the exploration of B. So I'll suspend the exploration of B by pushing it on my stack. And I'll choose, let's say, G as my current vertex. So I'll choose G as my current vertex, and now I'll move on to exploring G. Now let's list out the adjacent vertices of G. If we list out the adjacent vertices of G, we find that they are H, E, and B. So the adjacent vertices of G are E. See, E is an adjacent vertex, B is an adjacent vertex, and H is also an adjacent vertex of G. Now out of these three adjacent vertices, E has already been visited. As you can see, it has been marked as 1 in the visited array. This is step number 5, okay? Now B has already been visited, okay? H has not been visited, right? So what I can do is, before moving on to H, since G is my current vertex, I will output it, right? I will output G, I will mark it as visited, and I'll suspend its exploration by pushing it on the stack. And I'll set my current vertex to H. So H becomes my current vertex. Now I'll move on to step 6. And I'll look at the adjacent vertices of H. So what are the adjacent vertices of vertex H? I find that H is adjacent to F, B, and G. See, F, B, and G are direct links with H, have direct links with H, right? B, G, and F have direct links. So B, F, and G are the adjacent vertices of H. Now out of B, F, and G, I can see that out of B, F, and G, all have been visited. See, B has already been visited, so I can do nothing with it. F has already been visited, so I can do nothing with it. G has already been visited, so I can do nothing with it. Now, before proceeding, what I'll do is, since H is my current vertex, I will output it, and I'll also mark it as visited. Now, as you can see, since I have listed out all the vertices in my graph, my DFS is complete. But you need to show the backtracking approach. At least you can write it in your own words, how the backtracking will proceed. What will happen is, since there's nothing else which are adjacent to H and which have not been visited, you will simply pop the topmost element of the stack. Which is the topmost element of the stack? G. So you'll pop G and make G as your current vertex. And you look at the adjacent vertices of G. What are the adjacent vertices of G? E, B, and H. If you look at the visited array, E, B, and H all have been visited. That means you have nothing to do. So what you will do is, now again you will pop from your stack, and your topmost element was B, so your current vertex now becomes B. Now you will look at the adjacent vertices of B. The adjacent vertices are A, F, G, and H. You can see that A, F, G, and H all have been visited, so there's nothing you can do. Again you will pop from the stack. Your topmost element was F, so you'll pop it and mark it as your current vertex. Now you look at the adjacent vertices of F. The adjacent vertices of F are A, B, E, and H. Now all these 4 vertices have already been visited. As you can see in the visited array, A, B, E, and H have all been marked as visited, so there's nothing you can do. So you have to pop the topmost element of the stack, which was E, and make it your current vertex. Now again, what are the adjacent vertices of E? The adjacent vertices of E are A, F, and G. Now out of A, F, and G, all have been marked as visited in the visited array, so there's nothing you can do. And the topmost element of the stack is A, so you'll have to pop A and make it your current vertex. Now you look at the adjacent vertices of A. What are the adjacent vertices of A? The adjacent vertices of A are E, F, and B. Now all these 3, B, E, and F, have been marked as visited. That means all your vertices have been visited. Now, once your stack becomes empty, there's nothing more you can do, and you will come to the conclusion that your DFS traversal has come to an end. So the stopping condition for DFS is while the stack is not empty, you have to carry on the repeating steps. So this backtracking operation, which I explained just now, for your examination purpose, please write it clearly in your own words. Or what you can do is you can rewind the video from time to time and note down all that I have said. So I hope this video helps. If you have any doubts, please feel free to comment in the section below. Your feedback is what matters to me the most. Thank you so much for waiting till the end of the video. I'll see you in the next one.